तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We were looking at the log file of Xilink's place and route, and we will continue with the same now. And this is the Xilink's window which we had a look. We were in version 3 and revision 1, and we had run, and it has successfully completed the place and route, and we were inspecting the log report. From here we can see, so you can there is what is called utilities and one report browser there. If you click on this, you can get the report even after you closed after running the place and route earlier, and you can click one after another and inspect all this report, or we have already copied this log file here, and we were just mentioning that total equivalent gate for the design is just 1093 gates, whereas some additional gates are also required for JTAG compatible IO pins, and that is about 4000 gates that you need. And for larger design this will be much larger when compared to this, and we will just continue with this report. So we already mentioned that what is being reported at this point of time is that the device is being mapped, and for that a constraint file are also created. This is the constraint file PCF file created by one of the phases of place and route, and here once again it reports merely the number of clocks and number of slices. We have already seen what slices are, and in order to place and route, it all is an iterative process and requires a considerable amount of time, as we had mentioned earlier, and these are all this will keep going in a cyclic fashion. So as you see here, so you can see here the placer had tried already some 21,000 times. This is the first pass, and second pass more, and so on, and huge iteration even for a small design such as this sequential circuits, and you can see further. and once this is only the placing that has happened, and once that placing is done, so a file is also created here called a .ncd, which will be requiring for back annotation etc. later on. And it says there are no errors, and it was also doing place and route, and completely routed, it says here. You can even specify higher level of effort level from one of the menus in the place and route, and higher router effort level and placer effort. So that also can be changed as per your requirement. So more you do the iteration, more better results you will get in terms of frequency of operation. So that is the advantage in overriding the default. And here it gives the timing report. We have remember that we had already seen similar timing report in synthesis, during synthesis, and it was also pointed out that what was obtained there is only a rough estimate. Only Xilink's place and route is more realistic. It is closer to the real picture. We say it is closer because unless you map it, put your FPGA right on the PCB and run at your desired frequency and observe whether they are really functioning as per your functionality that you have programmed, and that is the final thing, final deciding point for you. And even here, in real practice, people have reported even a bettering of the report Xilink's place and route gives. For example, it may be 10 to 25%. A better performance also you can get based on real experience. So what they give is a guaranteed speed of operation here. And normally, as I mentioned, if the design is quite huge, what synthesis will report will be much higher frequency of operation than the place and route. So, and once the place routing are completed without errors, it will report here. And some timing errors it's saying, because we had specified I think 100 megahertz and it couldn't meet 100 megahertz. So here also timing error will naturally come, but this is not a handicap. You can once again the tool will report how much frequency of operation you could get and so on. So based on that we can see. And these are all the intermediate files. Right now we need not be concerned about it. And here comes the frequency of operation. You see it is surprisingly higher here. As I mentioned, for smaller design my observation is synthesis will be very conservative, for but real designs are all big. So it will be the reverse. So normally synthesis will report say 100 megahertz, but place and route can give only some 80 megahertz. So that is the usual scenario, whereas here it appears to be exactly reverse, and I think we started with 116 megahertz in synthesis. And here for final use in FPGA, you need a separate file called bit file, and it is also known as a bit stream. So that comes as an extension of bit. Dot bit will be the extension used, and it's a bit it's loading the design for this generation. And it also runs what is called a DRC. This is a design rule check. So, if there are no errors or warnings, it reports all that, and here it is creating this bitmap as I mentioned, and this is the output file. Because our design happens with sequential circuits, it merely takes and appends this dot bit and writes all this bit file here, creating bit. So, that is all to it for the log file. We will just go through this command summary which we have already used. So, we were just the second step. First step was to invoke the simplify and then go on to the design manager, that is a place and route, and we did not see the second step at that time, and we are just mentioning how to start the implementation place and route, and perhaps we did not read this. So, I will just read this out. Click on the dark arrow on the top left to start the implementation of the place and route. After it is completed, click on view log file and reports files to get implementation details. We have seen the view log file so far, and reports file, like I have showed browser, you will literally get exactly the same thing except for some more details such as what pins, what signals are mapped onto what pins, and will also be reported, and some timing report, all that we will be getting. So, we will see those reports as well. Files to get implementation details. If you are done, click OK to dismiss the implement status window, and an output file called sequential bits, this is what we have seen. Circuits.bit is created, and this file is downloaded into the FPGA housed on the target circuit board while checking your design on the hardware later on. So, this will happen only at the later stages of your design cycle. So, when the PCB is ready, only then you put on your FPGA and populate your bare PCB with different components including the FPGA, and then it will be ready for testing. At that point of time, you can download this bit file into the FPGA, and normally from the development system you have a provision to connect straight to the FPGA. You need a special interface for that, some serial interface or even a parallel interface. This file is downloaded into the FPGA housed on the target circuit board while checking your design on the hardware later on, and this file is what is supplied by IP core developer along with documentation. See, suppose you happen to be working for an IP core company. So, you as a designer will have to prepare a document, full document as to how the user can use it, and then also you should give this dot bit file. Normally this IP core people will not give the source file because they want to keep it to themselves, and unless the contract demands the otherwise. And next step, we will go on to Xilink's back annotation, and before this some of you expressed the desire to see the optimized Verilog files, that is a .vm file created during synthesis or simplify. So, we will see that, we will take up that first and then come back to this. This is the main simplify window, and this is the sequential circuits test bench, and in order to, there is absolutely no difference between the original, we need to invoke the model sim in order to see whether this optimized file, a .vm file is, of course here it makes no, this is only a test bench. So, what is different is the optimized file is only the design file. So, therefore, but the test bench includes that particular file. So, you have to have this. This is not really the correct way to do. Actually, should what we should do is we should go to the design file sequential circuits and then add okay, for the time being we will retain that, let us see. So, we will have to what I am saying is in the test bench you go and include earlier it was .v file design file, now what optimized file instead of the design file must be used. So, this is what it is here. So, in the test bench we have to include this .vm as I mentioned. This is a change from design file which was just .v to this .vm which was created during synthesis. This is the optimized file, and we can even have a look at this file if you wish later on. Right now let us open the model sim. It is already open, I think. Okay, it is open, and we are in the directory. Let us use pwd to reveal what directory: d user rum, d VLSI, etc. etc. It is not etc. Sorry. So, under this directory, I mean this .vm has been created in some other directory earlier, but I have already copied that into this directory, and in fact by directory we can find out whether it is so. It is already here, it is here. It is a huge file, some 42,000 and odd, and so now what we need to do is if you compile this once again. So, in this test bench we have replaced it with the .vm file. So, it will take this as a design file now and then compile. So, let us see what it says. Not to compile, design, compile, window opens, it is in etc window, and here we need all files at the bottom, then only you can view this. In fact, we do not need that also, because it can be Verilog itself. So, in which case after all what we need is only sequential circuits test, the test bench. So, we will just double click on this and watch what happens here in this window. When you double click here, you see it gave a big list, and I will read it for you. So, you are already familiar with the synthesis, having created LUT4, LUT2 and FDC, FDP, then once again LUT, D flip flops for FDP, etc. and so many LUTs, then mux, buffer, input buffer, output buffer. It has taken all this and compiled. So, that is because we have mentioned in the test bench .vm. So, earlier if it were .v it would not have reported all this. So, that means to say it has right now taken your .vm which was optimized file by synthesis as the source file, and next step is to load this design file. We do not need the compile here, so we will remove that, and this is the load file, and once again same buffer, all that primitives it is reporting here. I think towards the end you have sequence circuits underscore test. So, let us load this file. So, while loading also it has displayed all that primitive cells here, and there are no errors. So, we can conveniently see the waveform now. So, in order to see that, click view, then signals, then again view, then wave, then final last option signals in design. So, it has opened the wave file, you do not require the signals anymore, and if you click on this it will run. So, it has run and stopped, and as usual source file is opened at stop at terminated. So, you do not require this. So, this is the waveform that we have, and In order to analyze, we will take just one example, and in a similar fashion you can analyze other functionalities. So you remember we had this is a sequential circuit. We had, let us say, we had a counter, just a simple counter, which advances right from 0 through 255 and revolves around that, and it can be reset for certain conditions when counter is equal to 255, and can be advanced if ABC are each 1. So that's a simple counter. So we will just have a, I have already preserved the waveform, and as we had done before in Paint. So we will just have a look at that. So this is the waveform which you have already seen and analyzed earlier. So this is nothing but starting of the counter. For example, this is reset clock, ABC are the inputs, then reset counter here. Then advance counter, then counter next. Anyway, it's only a next value that indicates in advance, and this is the actual counter register. Notice that it is 0 here. This is what you have already seen, and it's advancing from 0, 1, 2, 3 and so on, and this is for advance being ABC being 1 here, and this corresponds to that. This we have already seen. Now what we need to do is, we have already run the simulation and captured the waveform for corresponding to the optimized file. So let us see what it is, and this is the optimized one. So I have named it as sequential count, same reg 1 I have preserved, and it is optimized, and this time based may be different because I had done it afresh, so that may be a different thing from that. This was here graduated like this, and here it is closer, yeah, it's not closer, I mean waveform is close, that means zoomed in, and you can see again this is the counter, final count value, and ABC are the inputs here. You can just see all other waveforms are precisely the same. Reset in clock ABC here, and you would notice one thing here. So in we have a reset counter as before, but there is no advance counter. So I think in optimization it might have removed that signal, because the same signal might be appearing elsewhere with some other name, because we had a conglomeration of different circuits. So that may be the reason. So I couldn't find that signal advance count. So that's why I was saying, while optimizing, a duplicate will not be created. So it will lift that one and use, it will be mapped just one time and then reused at different points of time. And here you can see again the counting advancing here. Now let us see what the is there a clock? I think I have forgotten the clock. Oh no, it's there. So the clock is this waveform here, and very last one is the counter here, and unfortunately you can't see both. Can you? With the difficulty you can, right? So now notice this here. See, at this positive edge of the clock, it's not happening, this counting. It is only after shift it has happened. That means to say, after all, the synthesis is aware of the delays, gate delays, because it has mapped onto the actual primitive cells that Xilink's place and route is ultimately going to use. So whatever place and route details supplied by Xilink's have been incorporated. So it may not be in depth, maybe interconnection delays are not fully accounted for, and that is the reason why we need to go for Xilink's place and route. So you have some sort of delay element also coming into picture, that is why you are able to see here. Let us see, compare this with the previous one. See, for example, so let us get to the clock. The clock is here. You may have to, it may be difficult for you to remember. So okay, let us take this here. Somewhere here I will just draw a line here. this is the positive edge of the clock, right. You can see it is exactly aligned with the same so any count change is exactly aligned with the positive edge of the clock here, whereas in the dot VM has a delay here, that is what we have seen here. Is it clear? And the counting as usual progresses in this fashion. Similarly, towards the end of the counter we can have a look and for both this. So, this is the original one and this is towards the end. Once again you can see at this edge, and when the count is 255, so this goes high. So, that is the reset count is acting here. Here you see this advanced count, but in optimized thing you are unable to see because it has been optimized, it has been removed, and the actual signal itself is not removed, but it may be preserved under some other name, not as this name. So, you see here right at 255, when the counter is 255, so it gives one reset output. That is what we have for resetting, is not it? So, as per this, it should reset when the 2 matches. So, coming to this, it is advancing, this you have already seen earlier, and again it wraps around the counter, and the optimized one corresponding to that is this, the clock is here as before, and all ABC are all 1 here, and so that it is count is advancing, that is the condition for advancing. From that we can make out, although this advanced count is removed in this. And last one is the count register. I have merely shown the last few counts, and once again you can see this reset counter is active when 255 is on, right. And notice the delay here also, when 255 has occurred, only after a delay, slight delay here, this is happening because this is being compared, right. And similarly here, when you go onto the clock, the rising edge is here, and 255 itself is maintaining the same phase shift here, right. So, this tells, I mean, in this fashion you can analyze any other circuitry that we have seen before, or create your own design and analyze. We are looking into the reports browser earlier prior to going for some diversion into the synthesis.vm file analysis, that is after optimization. So, we will resume from the place and route report browser. So, you have what is called utilities, and you have a report browser. If you click on this, so you will have a list of different report files. For example, you want to know, let us say we want to have a place and route report. So, this is the report. So, and then if you want just mapping alone, you can click on this map report, and then you have what is called translation report, navigation report, then pad report, IO pins etc. will be reported here. Some then delay report is available, then post layout timing report, and like this 2 are there. In fact, then one more you have called a bit gen report, and all these things are clubbed into one, we can say that log file which we have already inspected. I would rather leave it as an exercise for you to go into the depths of all this. Most of them will convey more or less the same information that you have got from the log file, and let us see one of this. So, for example, this is a pad report. So, this is the pad report, and IO pins will be reported here. The signal we had used in our design are A, B, C, D, then a flip flop, and then state machine, those outputs, a counter, and so on. So, all these are all the pin numbers for that. Pin number is here, pin name is also given here, and in this you may have so many other pins relevant to the particular FPGA, and for programming some reference and some ready and so on. There are so many pins there, even VCC, ground, all that will be there, because it is a full listing of all the pins pertaining to that particular package that we have used earlier. That is this is a device you remember was 100, speed 8 and PQ 240 package. So these are all the pins that you have already seen here. So pin 35, maybe there may be some rows, because it is only 240 pin, probably it is merely some deep type, or I do not remember really, and you can see some 237 pin number coming. So it is a 240 pin package. So naturally you should not see anything greater than 240 here, and each of these signals, whether it is an input or not, whether it is TTL compatible or let us see, then this is not clear to me, and how much load it can take, drive. So drive means so much load can be connected up to this much. I think maybe it may active low could be, and whether what is the speed, whether it is slow or not, then is there a pull up here, and so on. Then what is the voltage, any other constraint that we have here, and so on. So you can see voltage. This is pad report. Similarly, there are other reports, you can have a look at this. You have a question?
You said the level is TTL compatible, isn't it?
Yes.
Can we have other compatible levels also?
MOS, in fact these FPGAs are basically MOS base version. So they have what are called TTL tolerant voltages. The chip itself may be working at 1.5 volts or 3.3 volts and so on. So no matter what the supply voltage is, and they will have compatible IO, so that any other TTL or any other device, CMOS or MOS, can be connected. So coming back to this design manager here, so as I mentioned, you can use this utilities, then click on report browser, then you get you can open one file after another and find out what they are. If you are interested in say bitgen here, and let me have a look whether it gives any new information. Nothing much is there. So except that it reports it saving bit stream in sequential circuits bit here. So finally we will see place and route map are all almost same as log file, and here. So this is a timing file. So naturally all timing are reported in this. In fact, log file contains almost all of them here. Same clock timing it is reporting. So you can have a look all by yourself, it is not a problem. It is also called timing analyzer, and you can click various for various constraints, etc., and you get corresponding delays and so on. So next what we will consider is the back annotation. So we need to back annotate, because so far what we have done is only routed, placed, mapped onto a particular device, then placed and then routed it, and we need to get information for timing. So for example, you want get delays, so you need to have this what is called back annotated and .v file created finally. So for this you have couple of commands which we can execute in DOS mode, and and not in the design manager, but straight away from the DOS mode you can have. Okay, this little time consuming. There are commands here. I will have made into I have incorporated in the command summary, and I'll read out this one, and you have a question.
See, if my target frequency is achieved, I needn't bother what internal gate frequencies and all gate delays are, isn't it? So if my target is achieved, I just needn't bother about it.
In general, that is the case. Suppose you want to improvise. Suppose you have done and delivered the product. They say that it is malfunctioning at a particular time, right? Then you need to analyze. So how will you know that? Had you analyzed before, you wouldn't have got into such a mess later on. So it is a good practice. As a design engineer, we should go through the entire cycle. Don't leave anything to the chance. Yeah.
If the target frequency is, let's say, 100 megahertz,
yes.
Is it a good practice to see that it works at slightly higher frequency, or if I achieve 100 megahertz, it's enough?
As I mentioned before, this is a tricky thing, because sometimes it is observed whatever Xilink has reported as a maximum frequency of operation. Normally people have experienced 10 to 25% better performance, but some others have also experienced the other way. So one cannot say the best thing is to deal case by case. So for every design you will have to go through that. But how can you get that one unless you have gone through the entire cycle? If you bypass just because you want to make a quick bug there, so it won't really click. You have to go systematically step by step, so as to not to prolong your agony later on. Right? It's better if you sort it out right at the inception stage. In fact, while RTL coding, I mentioned that technological dependence, you may give some gates, even assuming synthesis tool keeps it intact. So even then, you have to go through all that and find out whether the total delay is really up to the mark. There may be some critical paths which you may take it light now, and later on that may blow out into a big problem. So it's always better to do it. After all, you are going to do only once in a lifetime for the product. So why don't you do it completely? And hardly it's going to be a couple of days, not more. And we'll continue with the we'll start rather the Xilink's back annotation. And the purpose of back annotation is to incorporate the gate delays, and then go on to the simulator and see actually the gate delays shown as a waveform there. In the timing diagram you can see the real delays, and we have already seen in the synthesis tool at in the waveform analysis prior to this, and that slight timing is affected in that even after optimization. So in place and route it must be more so. So I will just read out this one. Open a DOS command window. You need to open a separate DOS window because we want to execute in DOS command, and it is just a couple of commands only you need to run, but it is time consuming. Therefore I have whatever is the logging of that window, I have just preserved it here, and we will go through this step by step. After going through this step by step, I have actually run it just a few minutes back and captured on Paint, and we will see that version. Here it says open a DOS command window, change to the directory where your Xilink's place and route result files are located. Obviously you have to go into that directory because from elsewhere you have to give the entire path. So it's a good practice to just change your directory to the place where your P and R results are. And in the DOS prompt, key in the following command and execute to convert .ngd file to .nga file. So these are all intermediate files generated. As I mentioned, there are just two commands, one of which is already peeping here, and the purpose is to have two passes and get the back annotated .v file. So first phase is this here, and I will just read this. make sure that .ncd and .pcf files of the design are present in the current working directory. See, while running the Xilink's place and route, we had already got these files in that. So, I think it might be in one of these here. If you have a look, this is that revision 1 window, and you can see that .ngd here, and that is what we want here. So, ngd file to nga file we need to convert. Right. So, this is being done by this command. So, make sure that .ncd and .pcf, this is a constraint file that was also created. It is fundamentally the input is UCF file, you remember we had used as an input here, and the PCF files of the design are present in the current working directory. So, make sure about that, and the very first command for this is ngd anno. So, anno is annotation. So, it is first phase. So, I remember not the expansion for this one. It's just you get the back annotated file with this command. As I mentioned, there are only 2 commands here, and here the options are, I mean, you had to identify output file, that is how you identify here, and what do you want to create here is .nga file, that was what is indicated earlier, and some -p option also is required. I think it is for indicating it is PCF file. PCF is the constraints file created by Xilink's place and route, and that needs to be given along with .ncd file, and the output is nga file. And if you run this command, and I will show after both are covered, and then next step is second phase is you take this nga file which was created here and then convert it into back annotated.p file by executing the following command. So, here you have ngd to Verilog, BER stands for Verilog. So, you want to create a back annotated file which is nothing other than a .v file. So, also a Verilog file, and that file I have named it like this, just to discriminate between that original design and the back annotation. In case you are putting all this in the same directory, suppose you had forgotten this, it will overwrite that original file. So, you have make it a habit to indicate, if this is too long you can say BA or whatever, and then it starts from nga file which was created in the previous step, and that it takes as input and creates simply this here. So, it is just in 2 phases we should say, and we should also make sure I am sorry, the sequential circuit.sdf file is also created in this process. This SDF file is the one which has a delay information, is called standard delay format. So, this is also created here, and that is also important. And the next step is make a new directory and copy back annotated files. We have just .v file and .sdf file created, and also the test bench. So, if you have these 3 files, we can go to the next step. Let us see what the next step is, and here I will read it again. Make a new directory and copy back annotated files .v, .sdf and the test bench sequence circuits _ test.v into the same. So, then before going to this here, we will to the next step, we will just have a look at the window. So, in fact, this was what is the actual window which had run the this 2, but you can't read here. This one is the ngd anno -o, that is the very first command, and this after it has finished all this, it has given some warning also, which we will go into about some GSR and GTS. We will go into that shortly, and after that it has completed this. The second command was given here, that is ngd to ver, that is a Verilog, from nga to the back annotation file here. Once again it goes through, this is a time consuming operation here. It may take some 5 minutes or more, being a small file, but even that is quite a substantial time here as far as the presentation is concerned. And here it reports that Verilog SDF file sequence back annotate.sdf file is created here. That is what it yeah, I have, I think this is the one, right. The very same thing is copied right here, and that is what you see here. The very first command was, so this ngd anno -o sequential, all that we have already seen. Say that nga, then -p option, pcf, ncd, this is the command we had given. So verbatim is here, it is basically the same copy, and you can see that pcf file is being loaded here, and what device, all that is reported here, and it is saying annotating nga image and so on, and DRC check is also run, and here is the warning as I mentioned here. Some here you have to be very careful. Okay, so it's not a big thing. GSR and GTS, we will just comment it out later on in the next step, right. It is merely a warning there, and second command is here. So ngd var to sequence.nga, then this is the back annotated file here. Yeah. So it is reading the file, then flattening, specializing, design completed, all that it reports here, and once again some warning is there. So we had to look into the warning, should not just take it light. It says on block sequential circuits, some of them are missing or something, it is saying reconstructed because there are some missing bus signal here, right. So anyway, we are going to take this one into the model simulator, simulator, and verify functionality. So we don't have to read in between lines, right. And so finally, on SDF file is created here, writing into that it says, and that is completed it says, and then a netlist, Verilog netlist, that is .p. This is the file which we need, is created here, and once again some warning is given here, and finally it says some it is completed. It is only reminding of some procedure. So this warning is not a serious thing. So now what we will do is, we will go back to the summary and continue from where we left. Here I will read it out. Edit sequential circuits back annotated.b file and comment out two statements and as follows, and save it. So we need to identify this one. That was the last warning we saw there. That is what earlier also it had given. So what we need to do is, the last one he suggests another alternative. I have taken some other alternative. So in this alternative, what I am doing is, I am going to the back annotated file, editing that one, and merely commenting it here. I am terminating this after this. Originally this was not there, so this was equated here. So only two statements. In order to do this one, you can use find and locate that particular file. It is here. So you can use find, and then I just missed. It was already there, right. I think I don't have to see. This is back annotated file. Once again you can see LUT4, etc. All the primitives are there, right. Time scale, all that are here. If you want, you can just say find wire GSR, it will find it again. That is the one. So if you just want this here, so you can just see these are the two statements which I have already commented, right. And only after this step we can go for the next step. The next step is, in addition to this, you had to go to the test bench and then change. We had used .vm for that earlier, you remember, for that synthesis. Instead of .vm, it should be this back annotated file. So it is exactly the same thing we are going to do here, and again after this run the model sim. That is the next step here. So we need a little more time for this, and that we will cover. It is hardly another three more statements we need to go for, and if you have any question you can ask, because I am going to stop at this point of time. because this is going to be involved. So, we will see in the next lecture that. Have any question?
Why did you do that commenting out? Why did you do that commenting out?
That is because it has asked for some comments here. I will find out what that comment is. What it says is, please add Xilink's Verilog source glbl.v to your compile command, because these are all reserved words. Some library is will be invoked. So, unless that you specifically mention, it will not go there and pick it up. So, these are all mandatory requirements. So, either you can do the Xilink's way suggested or this way also. I preferred that way because it was easier just commenting it out, otherwise I had to key in this much, right. And at the time of, so the next step here is to take this back annotated file and go into the model sim and once again view the waveform, see whether the delay has been incorporated or not, right. We will continue in the next class. Thank you.